Welcome you all in this fourth talk on metric spaces. So, as we have seen several examples of a metric defined on Rn, and we have seen several metric spaces, namely L infinity, LP, S, and so on. And we have seen the space of all bounded real valued functions, and we have defined a metric D on BAB in this way that DFG is equal to the supremum of mod of f of t minus g of t, and then we have seen that the BAB with this D is a metric space. Now we consider in this talk we will see some more examples and some exercises related to the metric or metric spaces. So let us consider the CAB. Okay, let us denote CAB as CAB. Let us denote CAB as a space of all continuous real valued functions defined on the closed interval AB. Okay. So CAB is what? CAB is the set of all continuous real valued functions defined on the closed interval AB. Okay. And then we can take f and g, any two elements in CAB, and define the real valued function d infinity and d1 on CAB cross CAB as follows. The d infinity fg is equal to supremum of mod of f of t minus g of t as this one. Okay. The second we can define d1 fg is equal to the integral from a to b mod of f of t minus g of t. Here is where the integral is the Riemannian integral, which is possible because the function f and g are continuous on AB. Okay, so a, f and g are continuous functions, and this is a Riemannian integral. Then we define in this way. Then again, because by using the property of the mod function, we can prove that this d infinity, okay, d infinity, this function d infinity and d1 functions, these two functions are matrices on CAB. So these two are matrices on CAB. Now what I am asking or what I am saying from the very beginning, how we can calculate the distance between any two functions. So here we are having the CAB is the space of all continuous real valued functions defined on the closed interval AB. So the question is, what is the distance between these two elements, between any two element in this space? So for that we have defined the metric d infinity in this way and d1 in this way. Now what does it mean? The meaning is that the distance between f and g, okay, is this is the longest distance between these two functions. So suppose this function is your f1 function and this function is your g function, then this is the longest distance between these two functions. Okay, this distance is the distance between f and g. Now what does it mean? The meaning of this integral from a to b, meaning is that the area covered by, if this is your g function and this is your f function, this is my function f, okay, this is my function g, then the area bounded by the a and b, so this area, okay, because we have defined d1 fg is equal to the integral from a to b mod of f of t minus g of t dt. So the area bounded by x is equal to a and x is equal to b, and these two functions is the distance between f and g. So this is the way to calculate the distance between any two functions. So one way is we can calculate the maximum vertical distance from the point t f of t to t g of t. Okay, so this we can calculate as we have seen in the previous graph from this vertical distance, this one. So this can be calculated by using this formula, and this can be calculated by using this formula. So these are two different ways to calculate the distance between any two functions. Now, can we define some other kind of distance function on CAB? Yes, we can do. We can define if f and g are two real valued continuous functions defined on the closed interval AB, okay, then we can define a function d, okay, from CAB cross CAB in this way, that dfg is equal to integral from a to b mod of f of t minus g of t raised to the power p dt whole raised to the power 1 of p. Then we can also see that this D is a metric on CAB, and CAB with this D is a metric space. So you can see that we have defined three different kind of matrices on CAB. Keep in mind, again I am repeating, we can always define a discrete metric everywhere. On every non-empty set we can define a discrete metric. Let us see here is now the question is that here is we have defined this metric d1 is equal to integral of this one. Okay, here is we are taking a CAB, the f and g are element of CAB and we are considering the integral. This is the Riemannian integrable. The functions are Riemannian integrable. Okay, now the question is that if these functions are not continuous, then whether this is a metric or not. Okay, so instead of taking CAB, let us consider x. Let's consider x is the set of all Riemannian integrable functions on AB. Not necessarily the element of x are continuous. The x is the set of all Riemannian integrable functions on AB. Okay, and then for any f or g in x, dfg, d is defined in this way, that dfg is equal to integral from a to b f of x minus g of x dx. Okay, of course, if f and g both are continuous, then this is a metric on a CAB. But if f and g are not continuous, f and g are only Riemannian integrable functions, then G is not a metric on x. Why it is not a metric on x? We can take f of x is equal to 0 when x is equal to a, and f of x is equal to 1 when x lies between a and b. It means that the function f is not continuous. It has a discontinuity at x is equal to a. Okay, so the function is not continuous. And let us consider the function g. G is equal to gx is equal to 1 is a constant function, and so it is continuous. So the f is not continuous, but f is continuous. Now let us calculate the dfg by using this formula. So when we use this formula, what will happen? It will be equal to 0. We will see that of course if x is equal to a, then it is equal to 0. So f is equal to a, then this is equal to 0. Okay, and for all this is equal to 1, and take limit from a to a, so this is equal to 0, and when it lies between a and b, so this is equal to 1 and this is equal to 1, so it is equal to 0. So in all the cases the distance between f and g is equal to 0, but we can see that f is not equal to g. So it does not satisfy the property of a metric which says that dxy is equal to 0 if and only if x is equal to y. Okay, so here is weak, and now you can see that except this property that dxy is equal to 0 does not imply x is equal to y. It's this d satisfy all other properties of a metric. Okay, so if a metric, if a function d which satisfies all the properties of a metric except the one which says that dxy is equal to 0 does not imply x is equal to y, then such kind of the function is known as pseudo metric on x. So the definition of a pseudo metric on x is the following. Take x is any non-empty set and a real valued function d defined on x cross x. Okay, this function t is said to be pseudo metric on x if it satisfies the following condition. Following condition is dxy is greater than or equal to 0, which is same as m1. Here is only dxy is 0 if x is equal to y. Here it is missing the if and only if. This is equal to 0 if this is x is equal to y. Okay. The second thing is that it is not given that if dxy is equal to 0 then x is equal to y. So this property is missing. Okay, so if this property is missing, the third one is the symmetric property is the same as in the metric, and the fourth property is the same as the triangular inequality. So the property, what property is missing? That if dxy is equal to 0 then x is equal to y. Only thing is that if x is equal to y then dxy is equal to 0. So if the one property this if a function, real valued function d on x cross x satisfies all these four properties, then this d is called a pseudo matrix on x, and the set x with a given pseudo metric d is called a pseudo metric space. Okay. Now let us take some examples here, and then we will come to some more exercises. So first let us take x is equal to R2. So let us take x is equal to R2, and x and y are any two elements in x whose coordinates are x1, x2, y1, y2 respectively, and we define dxy is equal to mod of x1 minus y1. Can you think that mod of x1 minus y1 is equal to dxy is equal to mod of x1 minus y1? Keep in mind, in R2 we have defined dxy is equal to mod of x1 minus y1 plus mod of x2 minus y2, and we have seen that this is a metric on R2. But if we consider only dxy is equal to mod of x1 minus y1, or if we are considering only dxy is equal to mod of x2 minus y2, then would these two functions be matrices on R2? So as you see that we have defined dxy is equal to mod of x1 minus y1 plus mod of x2 minus y2, and this is a metric on x. But if we are considering only that dxy is equal to mod of x1 minus y1, or we are considering another metric d tilde dxy is equal to mod of x2 minus y2, would d and d tilde be metrics on R2? No. You can see why it is not. So if we are considering this one, then d is not a metric on x. Then d is not a metric on x. However, it is a pseudo metric on x. Why? You can take x is equal to 0, 0, y is equal to 0, 1. okay, and then of course x is not equal to y, but the distance between them by using this formula is equal to 0, because if you take dxy, then here is equal to x1, this x1 and this is y1, so x1 y1 is 0, so this is equal to 0, but x is not equal to y, so this is not a metric. And for this one you can consider x0 0 and y you can take 1 0, and then you will see that d2 is not a metric. So it is, and you can see that it is not a metric on x, but it can be easily checked that d satisfy all the other properties of a metric, okay, and therefore this d is, and same as this d, both they are the pseudo matrices on R2, but not a metric. Keep in mind, I am taking this. I will show you why I am emphasizing on these things. Okay. Let us do some exercises, okay, before ending this section. So first, if suppose xd is a metric space, then prove that this inequality holds good. Okay, that's it, mod of dxz minus mod of dyz is less than or equal to dxy. So this you can prove very easily, no problem. How can you do it? Basically the meaning is that when you take the mod here is then it means that it is same as to say that minus dxy is less than or equal to dxz minus dyz is less than or equal to dxy. So you will have to prove this one. So one way you prove this thing, and then the other way you prove this thing, and then from there you will see this one. So this you can do. How we can do it? We can do it in this way, that dxy dxz is less than or equal to this one. This is by the triangle inequality, okay, and of course instead of writing x, we can write it, you can take this we can write dyz, okay, is less than or equal to dyx plus dxz, okay, again by the triangle inequality here is, and now here we can use the symmetry property. So by using the symmetry property we can write this, and this is same as this one, and therefore you can see that dxy you take on the left hand side and dyz you can take on the right hand side. So we can write this is less than or equal to this one, okay, but again this from here you can see that dxy, okay, so dxy is greater than or equal to dxz minus dyz. So dxz minus, so this is greater than, so this is less than or equal to this one, and then you can see that this is, so we have this thing, and then from here you will get this answer. That is the answer, is very easily. Now we can prove now the next question exercise is that prove that d mod of this is less than or equal to d mod of dxy minus dzw is less than or equal to dxz plus dyz, okay, and this also you can prove by just by using the properties of a mod function. So this we have seen that just we have seen here, the dxz minus dzy is less than or equal to dxy, okay, and of course we can also have this one and these two one, and now we can combine these two things, we will have the result. So it is very simple way. Now a very important thing is that suppose x is your any non-empty set and d is a real valued function, okay, we satisfy the following three properties, okay. Now what is missing? So then we have to then prove that D is a metric on X. So D is a metric on X. So what is the property is missing here? The property is missing here is that dxy, here is the property is missing that dxy is greater than or equal to 0. So you will see that this property can be achieved from rest of the three properties. So how you can do it? So instead of m1, m2, m3, m4, if somebody is writing that a function d from x cross x to r is a metric, if it satisfies these properties, even then it is okay. In some books you can see that this property is missing. This property basically is automatically follows from the rest of the three properties. Okay, so how you can find? You can put y is equal to x in this one, and then you will see y is equal to x, so both it is equal to 0 because 0 is equal to dxy, and then here dxz plus dzy, and now you can use the symmetry property, and then you can see that 0 is less than or equal to 2 times dxz. Okay, so it means that dxz is greater than or equal to 0 for all xz in x. So this is holds good. So this way is you can prove that dxy is dxz for all xz in x is also holds good. Okay, so the first M1 follows from the rest of three properties. Now, instead of this, let us take a little bit more. If x is your metric, x is or any non-empty set x, and d is the real valued function which is defined in this way, that dxy is equal to 0 if and only if x is equal to y. And now in the third triangular inequality we have like this, dxy is less than or equal to dzx plus, I am considering here is dzy. Okay, keep in mind I am not considering here is dxy. In the triangular inequality you have dxy is you have the triangular inequality that dxy is less than or equal to dxz plus dzy. But here you are taking dxy, okay, and instead of this I am taking here is dzx, and this is same as this one. Okay, then even then if you have like this, keep in mind the triangular inequality is quite different than the triangular inequality given in the definition of the metric. So what is the problem? So here is this is the same, okay, but here is the problem is that we do not have the symmetry condition. So we will have to prove that the symmetry condition. If we can prove the symmetry condition, then this can be written as a dxz. Okay, here is dxy, so dzx can be written as dxy, and then we will get the symmetry condition, and if we, and also we will get the triangular inequality. So we will have this one, symmetry condition means all these three conditions, okay, in the previous exercises, and from here these exercises we can see that D is a metric. So we need to prove that if these two conditions are satisfied, then D is a symmetric. So this you can prove very easily. Okay, how can you prove this one? Let us take you can take z is equal to x. Okay, z is equal to x, then z you will not get anything. So here you held z. So okay, so you take z is equal to y. Take z is equal to y. Okay, so you will get xy is less than or equal to dyx. Okay, yes, you can take this one, and then same way you can substitute something else. You can prove that dyx is equal to greater than or equal to dyx, and then you will prove that dxy is equal to dxy is equal to dyx, and then you can prove that it satisfies the symmetric condition. So by using this one, you can see that you can prove that D is a metric on X. Now, instead of this, okay, instead of this, okay, here we have this one. Now, instead of this dxy is less than or equal to dz, if I put here is dxz, okay, if I put here is dxz, even then it would be a metric. So if D is a function defined from x cross x to R, we satisfy the following condition: dxy is equal to 0 if and only if x is equal to y, okay, and dxy is less than or equal to dxz plus dzy. It means that we have the triangular inequality, we have the second inequality, but the symmetry inequality is missing. So, but by using these two, we cannot achieve the symmetric inequality. But if here we have dzx, then we can achieve the symmetric inequality. But by using the triangular inequality, we cannot achieve the symmetric property, and therefore we can see that a function, okay, D which satisfy only these two properties may not be a symmetric on X. Okay, let us take here is I have just considered any 2 point x is equal to this and y is equal to this, and just then you can find the distance between x and y by using different kind of matrices defined on x is equal to R2. Okay, the same way is I have this, we have this is the C is the space of all convergent sequences. Okay, small c we denote by small c the space of all convergence sequences, and the metric is defined on C in this way, where x and y are sequences, and then we can see that this D is a metric, and you can prove very easily. Now, the important thing is that suppose you have a D is a metric on X and alpha is greater than 0. Then D1, another metric you can define by using the previous metric D and alpha, like this, alpha times dxy. Then this would also be a metric on X. Instead of dx2, we can define that minimum of 1 and dxy. Minimum of 1 and dxy. Then this would also be a metric on X. Now again, my question is, what will happen if instead of minimum, I am considering the maximum? Can you say anything? Would it be a metric? Try, check. And if D3 I am defining matrix which is equal to the square of dxy, then of course this is not a metric. Why it is not a metric? Because the a square plus b, a plus b whole square, because this is the square, okay. So this is equal to the a square. So this, the third triangular inequality does not satisfy for this function. The other properties are holds. First hold, second, third, symmetric hold, all the properties hold except the third one. So here is third one does not hold, and therefore this is not a metric. Okay. Now, let us take another exercise. So if suppose K is the set of all real or complex number, all the time this K is denoted by the set of all real or complex numbers, and we define dxy is equal to 0 if x is equal to y, and this is equal to mod of x plus mod of y, and then you can see that this d is a metric. And now you try to find out and prove that this is a metric on AB. And here is you take x is equal to 0, 1, okay, define this is the usual metric on x, then d is a metric on x. Similarly, the set of all rational numbers and dxy is equal to mod of xy. By using the properties of mod, you can define that you can prove that d is a metric on x. Okay. In the same way, if you have the set x of all real numbers which are strictly greater than 0 and define dxy is equal to mod of 1 over x minus 1 over y, then d is a metric on x. Now, if I define x is equal to r, set of all real numbers, and I define the function dxy is equal to square root of mod of x minus y, okay, then this d is also metric. Okay, the only thing is that the first property is m1, m2, m3, or only you will have to prove that this triangular inequality. So for the triangular inequality, you can take the square both the side and then use the property of the mod, you will get the answer. Here you have suppose x is equal to set of all rational numbers, okay, and p upon q, r upon x are rational numbers in their lowest terms, okay, and define q, okay, the d distance from p upon q, r upon s is equal to 1 upon q minus s upon s. Then would it be a metric on x? You can see that if I consider here, I gave the 1 over 3 and 2 over 3 are two rational numbers.
No, sir, card. I have to take the card. So you have only 5 minutes left.
So you have x equal to this, you can take these two numbers in their lowest term, and then you will see the distance between 1 over 3 and 2 over 3 is 0, but the 2 points are not the same. And similarly, you can prove that the set of all irrational numbers, okay, with this metric is, but you can see that if this is irrational numbers, then this is a metric on x. If you have set of all complex numbers and d is defined in this way, then prove that it is a metric on this one. Determine whether these are the matrices on R or not. You have to check whether this ln x minus y, if x is equal to y, okay, then the ln 0, so it will be equal to 0. So it will just you find out the first 2-3 properties, you try to check, and you will see that the sum of satisfy all the properties. You go for the last one, for example, if you are taking this one, okay, only then you have to go up to the triangular inequality. But from the rest of, you will get the answer within 1 to 3 properties. Here are several other questions, exercises, where you can prove that this dx is equal to r defined in this way is a metric on x. The metric defined in this way is a metric on R2. It is called jungle river metric. The metric defined in this way is a metric. I have given some hint, so you can do by yourself. And then you see that if I take the minimum, I told you if you take the maximum, then if it is I take the minimum, whether it is a metric or not. And now you see that if I consider x is equal to this 2, 3 and y is equal to 2, 4, then x is not equal to y, but the distance is 0. So d is not a metric. Okay. Similarly, there are some other you can take like this is not a metric. Okay. D infinity you can define, calculate the distance. So you can do this one. Here is also you can see if d1, d2 are matrices, then check whether d1 plus d2 is a metric. Okay. And maximum of d1 plus d2 is a metric, and minimum of this and this, they are matrices. Here I have given some things which you can see that the triangular inequality does not satisfy. Okay, so these are several exercises. Okay, here I have some more exercises, and then you can see that in several cases you can check whether the metric is, but the important thing is that from here you can see that if dxd is a metric space, then with this d you can define another metric in the following way, that is d infinity is equal to dxy divided by 1 plus dxy. So this way you can define another metric, and here are some other exercises and that you can do. And okay, thank you very much.